This last set of notes is kind of a catch-all in order to help you guys remember a bunch of things that we learned throughout the notes on the different types of bonding. The first type of bonding that we're going to talk about is the metallic bonding. That's when you have one or more metals and they kind of share all their electrons in this weird sea of electrons. That's supposed to be an A. Sea of electrons. And that sea of electrons is because the electrons are mobile. Those are two ways that they refer to the electrons in metallic bonding on the exam. You can find metallic bonding as mostly solids at room temperature, but also there's one liquid. And hopefully you've already memorized it. That is mercury. There is one liquid metal at room temperature. Metals always conduct. Doesn't matter if they're solid or liquid. They conduct electricity and they conduct heat, so they're always conductive. Also, they are malleable, which means they're bendable. They are ductile, meaning they can be pulled into a wire. Those are things you've already memorized from when we talked about them in the periodic table. The next section we're going to talk about covalent bonds. Covalent bonds are referring to molecules. This is when you have at least two nonmetals bonded to each other. They can be found as solids, liquids, or gases at room temperature. They have relatively low melting points and boiling points. So they melt and boil at relatively low points. They never conduct electricity on their own. If it's covalent, meaning that it's got nonmetals in it, it's not going to conduct, and that makes sense. It has nonmetals. Nonmetals are not conductive. And then the last thing, they're characterized as being relatively soft. They're not very hard, especially when you compare them to the next section, which are ionic bonds. Ionic bonds are when you have a metal bonded to a nonmetal, characterized by not sharing, like up in the covalent. This is sharing electrons, where here it's a transfer of electrons. They are always solid. The arrangement of the atoms in an ionic substance makes it so they always have to be solid unless you get them really, really, really hot. They have really high melting points and boiling points. It takes a lot of heat to melt or boil them. The only time they conduct is when they're melted or dissolved. And that kind of makes sense because when it's melted or dissolved, that kind of frees those metals up along with their electrons to make them mobile. If you're ever asked to rank them by their melting and boiling points, you use the electronegativity difference. The higher the electronegativity difference, the greater the melting and boiling points. And then the last little thing I want to talk about, sometimes they ask about compounds that include both metallic and covalent bonds. This is any compound that has a polyatomic ion. So if it has a polyatomic ion in it, that ion is actually constructed of covalent bonds, and then what it's bonded to is bonded by ionic bonds. So let me show you an example. Sodium hydroxide is a strong base that we use often in lab, and sodium has a +1 charge when it's bonded. And hydroxide is a polyatomic ion with an overall charge of -1. Since within this polyatomic ion we have two nonmetals, the bond between them is covalent. But the attraction between the sodium ion and the polyatomic ion hydroxide is ionic. So within this, it's covalent, and then between the two, it's ionic. Another example might be ammonium hydroxide. We have NH4, ammonium, and then hydroxide, OH minus. Now we have two polyatomic ions this time. Here we have nitrogen and hydrogen, both nonmetals, so within this it is covalent. And we have oxygen and hydrogen in the hydroxide, again both nonmetals, so within that it's covalent. So within each of these it's covalent. But between the two, because of their charges, this +1 from the ammonium and the -1 from the hydroxide, it is ionic. So if you're ever asked which of the following has both ionic and covalent bonds, pick the one with the polyatomic ion.